This presentation is all about what happens once the pumps have been installed and the customer gets on the phone to you and said, there is something wrong with the pump. And we've all heard that many times before, I'm sure. So we're going to look at pump troubleshooting, the common things that customers get on the phone to us and complain about. We're going to scratch our heads and think there must be something wrong here. So we're going to look at the various things that they report. The pump's not discharging, or it's not discharging enough. The flow rate is down. Those are the sorts of things that they report to us. And from experience, we can see that that is probably due to one of a series of possible causes. The first one is the pump's not primed properly. Now, in the earlier presentations, I've all told you that the pump suction needs to be primed. That means no air in the suction. If you've got air in the suction, you're not operating properly, and you may have a situation where you're not delivering the full volume from the pump. Alternatively, you may have a situation if it's not primed at all, it will just spin and not deliver any fluid. Wrong direction of rotation. Remember, with a three-phase motor, it's capable of spinning in both directions depending on how the wires are connected. As far as the pump concerned, it's a unidirectional machine, and we must match the sense of rotation of the motor to the pump. If the driver's speed is too low, then we will not deliver the volume that we're expecting. We choose the pump based on a particular speed of operation, and in that situation, we choose the duty point. So if we run the pump slower, we will get a lower delivery. It could be that the system head is higher than we really calculated, because remember, when we select the pump, we haven't built the system. We're dealing with system on paper, and it's very often the case that we get the head calculation wrong at that design stage. So if we've undercalculated the system head and the actual head is higher, we will go back along the pump performance curve and we'll get a lower flow. Air entrainment in the suction line will also affect the performance of the pump, and it will give us a lower flow because we're not pumping an incompressible fluid. When we've got air in the system, it's a combination of liquid and gas, and therefore is compressible. And then finally, we could have a blockage inside the pump or in the strainer. All of those things can affect the output of the pump, and that is what your customer is complaining about. So those are typical of the troubleshooting methods that you can use, and by a process of elimination, talking to your customer over the phone, you can get him to check those items, and you don't necessarily have to visit site to solve that problem. The next thing that customers complain about is insufficient pressure. And we've already gone through procedures to determine what the pressure is at a particular flow rate by looking at the performance curve. So if our system head is lower than we calculated, our operating point will be at a lower head than the customer might have specified in his order. But we can't change that. The pump will always operate where the pump curve intersects with the system curve. So if they got their calculations wrong, the pump will not recognize that. Wrong direction of rotation again. That will affect the head, but it's not as bad as affecting the flow, because the head is related to the impeller diameter, whereas the flow is related to the vane angles of the impeller. The speed too low. We know that the head is directly proportional to the square of the speed. So if we drop the speed down lower than we actually designed, it will have a square law effect on the head. The impeller diameter is too small. We've taken too much off the impeller when we trimmed it. Again, we might not have gone through our calculations correctly. Air entrainment, again, is important in terms of developing the head, because we've talked about the compressible impact of the air in the fluid. And finally, the impeller might be worn at the seal ring areas. We've discussed that in earlier papers. that the seal ring clearance is very important for maintaining head. And if it's worn in those areas, we might have to think about changing the wear rings on the impeller. Okay, problem number 3 that we get reported is excessive power. Now, power is generated for hydraulic reasons and mechanical reasons. If we look at the hydraulic reason, cavitation is unstable operation of the pump, and it causes a big demand for power. So the power goes up rapidly as soon as the pump is in cavitation mode. If the system head has been calculated incorrectly, again, we're going to need more power to overcome that head. If the speed is higher than we use for pump selection, again, we'll need more power because power is proportional to the cube of speed, pump speed. Do you remember we did that when we looked at affinity laws? So we can see that it will have quite a big impact. The specific gravity of the fluid might not be one. We normally select pumps based on curves, and those curves assume that we're pumping water at 15 degrees C or 25 degrees C, something like that. So if we've got pumping a liquid that's got a specific gravity greater than 1, we will need more power. The impeller might be binding inside the casing. We talked about them when we were talking about alignment. We have to make sure that the impeller rotating element is concentric with the casing, otherwise there's a possibility of pickup. And then finally, we could have a bent or misaligned shaft that's causing binding in the bearings, and therefore we've got higher power draw on the motor that's driving the pump. Finally, the other complaint that we get from customers is excessive noise. And again, the noise can come from either hydraulic reasons or mechanical reasons. Cavitation, that's a very noisy process, okay? Insufficient submergence causing air entrainment into the pipeline can cause noise. A block strainer is going to affect the losses in the suction system, and again will make the pump noisy. A bent shaft or shaft misalignment can make the pump noisy from the bearings. The driver running faster than expected might cause more noise from both the pump and the motor. And loose parts or pump mountings not rigid can also cause vibration. Most common, though, is lubrication failure. And lubrication failure means that the bearings are going to get noisy and eventually fail. So that's something that we need to try to avoid. In order to get an idea of what is actually going wrong with the pump, we need to collect data. How is the pump operating? Where on the curve is it operating? And we can collect that by having fairly simple instrumentation. We require an accurate determination of the site conditions. Again, we talked about this earlier. Site conditions are very important to the correct operation of the pump. Visual inspection of the pump mounting, suction pipe work, and so on can tell us a lot about the possible cause of faults. And in this day and age, we can get a situation where people can take a photograph of the installation and they can text it to us and we can have a bit of a look and see what's going on. You have to be able to measure the key parameters. You can't often measure flow because there isn't a flow meter in the circuit, but you can measure pressure and you can measure power absorbed. There are instrumentation usually in the control panel that allow you to do that. And from that, you can get a picture of where the pump might be operating on the curve. And you can determine the pump operating points from that data to see whether it's in that preferred operating zone that we've talked about before. So we compare all that data with the original pump selection criteria, and if there's a mismatch, then chances are that that's going to be the reason we've got problems. So we analyse the problem and then we can generate solutions.